Thank you. Good morning, everybody. It's a pleasure to be speaking here in this third winter AI school organized by NAAMII. Today I'll be covering foundations of natural language processing, and then within that I'll be covering the basics of natural language processing and the pipeline. Right, so basically natural language processing is all about solving sequencing tasks, right? So these two things will be covered in the first part of the talk. In the second part of the talk, I'll be sharing a little bit about my own research, particularly one particular project that we completed in the 2020. All right, so I'm Bal Krishna Bal, and I'm currently Associate Professor and Head of Department at the Department of Computer Science and Engineering, Kathmandu University. Sure, thank you. So let's get started. We are already a little bit late than the scheduled timeline, so let's get started. And this would be the contents of today's first part of the talk, in which I'll be covering the foundations and the pipeline, basically, right? I'll be introducing NLP in general, and then talking about a little bit on the NLP applications in the real world, the NLP tasks, the building blocks of a language and their applications, the challenges of NLP, and then what machine learning, deep learning, and NLP, how are they related, right? And then the approaches to NLP. So this would be part one, and in the part two, I'll be covering NLP pipeline, data acquisition, that is how you acquire the data, and then the several pre-processing steps like text extraction and cleanup, right? And then feature engineering, followed by classic NLP ML pipeline, the deep learning pipeline, followed by model development, evaluation, and post-modeling phases. So this would be the basic outline of my the first part of my talk. So let's get started. So natural language processing is the short form of natural language processing, right? It's a subfield of artificial intelligence, that's AI. That's the broader NLP, broader discipline is AI. That's the superset, whereas NLP is a subset. But as you can see from the figure as well, there are several interrelated sub-disciplines, and these being namely linguistics, mathematics, computer science, neuroscience, statistics, and so on. So NLP, as you can see from the figure as well, comes as an intersection of all of these interrelated sub-disciplines of artificial intelligence. All right. So NLP has the famous, has the roots to the famous Turing test, right? Conducted by Alan Turing, and basically NLP deals with the ability, making the machine understand natural language, and at the same time enabling the machine to generate human language or natural language in the same quality as we humans communicate with each other. So it has broadly two subcomponents. So that's natural language understanding. It's about making the machines understand our language, the natural language, and natural language generation. That's NLG, and it's about making the machines generate natural language in the same quality as we humans communicate with each other. So this is the basic evolution of NLP research. That's the timelines, right? It starts all the way as early as 1950s, right, and moves all the way till 2021. That's now, right? So the early systems were rule-based systems, right? Gradually the focus moved to the statistical models, and then lately the trend is, of course, machine learning and deep learning models. Okay, so that's the evolution of NLP research, or the timelines of the NLP research history. So what are some of the applications of NLP in the real world? Because we might be interested to know why NLP is getting more and more prominent in our daily lives, right? So NLP in the real world, talking about NLP in the real world, there are several core applications. One of them is the email platforms, of course. So all of us use the email platforms, right? And we get troubled by a lot of spam emails that come into our inbox, which is undesirable, right? So the first application would basically start from there, right? So email platforms using NLP to implement spam classification, priority inbox, calendar event extraction, autocomplete and all, right? So that's one of the prominent core applications. The other is voice-based assistance, which is getting increasingly popular, right? We use the voice-based search engine facility or application on a daily basis, right? We give commands to the virtual assistants and make it do certain tasks for us, right? So voice-based assistance is another prominent application here. All right, I've already talked about search engines, and then this machine translation service, which has matured over the years now, right? So one of the example is Google Translate. Google Translate, which now supports 100+ languages, right? So that's one of the applications. There are other applications, right? So social media is getting more and more vibrantly used by everybody, right? And with that, there are applications which use and analyze the social media data, right? So extensive use of NLP in e-commerce platforms like Amazon, for example, right? So there is this analysis of the buyers' trends and then the certain recommendations that's being provided to the buyers, right? Based on his or her purchase histories and all, right? There is an increasing trend of use of NLP in other domains like healthcare, finance, law, etc., right? The spelling and grammar checker correction tools. So all of us use editors, right? And then all of us are also familiar, I assume that familiar about Grammarly. That's an application which basically checks the grammar and all those stuff, right? So NLP is basically a backbone of all these different applications, natural language processing. We must have certainly heard about IBM Watson, that particular AI, that particular bot who won the popular quiz show Jeopardy, right? So NLP has basically advanced from its primitive states to really advanced form right now, right? So NLP is used in a range of learning and assessment tools and technologies, automated scoring in GRE exams. That's quite an advancement. Plagiarism detection, right? So we in academia, we are concerned that the assignments submitted basically aren't copied from somewhere else, verbatim or without citations. So plagiarism detection, the Turnitin app, that's very popular and very successful example of natural language processing. ITS, that's intelligent tutoring systems, right? We have, all of us have used the learning management systems in some way or the other, Google Classrooms, the Moodle and others. So there are these intelligent tutoring systems also in place, and which are applications of NLP, right? So there are basically NLP also is building large knowledge bases like Google Knowledge Graph. So these are some of the applications. Other application would be language modeling. So each language has its own structure, right? Each language has its own structure, meaning English, for example, follows this subject, verb, object structure, SVO, right? As in I eat rice, whereas Nepali, for example, follows a subject-object-verb structure, SOV, as in ma bhat khanchu, for example, right? So each language has its own language model, and this language modeling is basically used for predicting the next word in a sentence based on the history of previous words, right? So we know that the Gmail, for example, this has this feature whereby it suggests some auto completion facility in which you just type something and then it tries to predict what you are intending to write, right? So that's autocomplete. That's another application here. So language modeling is basically a very powerful feature, right? Or feature that's used in a variety of NLP tasks or problems like speech recognition, optical character recognition, handwriting recognition, machine translation, spelling correction, and several others. The other tax, language modeling is one of the tasks of NLP. The other tax is text classification. I was talking about spam emails, right? And spam and ham. That's an example of classification, right? And then there is also this sentiment analysis. Sentiment analysis, which was a boom in the early 2000s. It still is developing, right? It's basically about analyzing the sentiments expressed by the users over a product, for example, or over some politicians, or over some certain services, right? Whether the people are satisfied about the service or not. That could be positive, negative, or even neutral, right? So spam identification, sentiment analysis, all these fall under text classification problem. Information extraction, that's another task, right? That's quite a useful task. So from a body of text, we'd like to extract certain information, right? It could be proper nouns, it could be some calendar events from emails, for example, names of people from social media posts. So that's information extraction. Information retrieval, that's another task. And talking about search engines, information retrieval has a close relationship with that, right? So every day we use Google and all the search engines, and we'd be interested in finding relevant documents based on our search query terms, right? So that's information retrieval. Conversational agent, right? Typically in a task like question answering, right? In question answering, you basically hold a conversation with the agent, right? And based on that, you get some answers to your queries, right? So Alexa, Siri, Google Assistants are some of the common applications here. Text summarization. So we live in a busy world, and all of us are busy. So we don't have much time to go through all the text. And what is desirable is that we get a gist, a summary of the text that we are interested in, right? So text summarization is that example, which basically helps us to get the gist or summary of any text. It could be from single text, or it could be from multiple documents or multiple text as well. Yeah, question answering, that's already, basically I'll talk to you about it. Tasks of building a system that can automatically answer questions posed in natural language, right? So basically we'd want to pose any queries that we would have in our natural language, and desirably we'd expect the machine or the software application to answer in the natural language as well. Machine translation, Google Translate is an example here, right? So we'll have a source language, that's English, for example, and the machine translation system would provide the output in the target language, that's Nepali. So that's another application or tax here. Topic modeling, right? So essentially, topic modeling, what it does is that given some texts, right, it automatically tries to suggest the topics covered by these different texts, right? This is a task of uncovering the topical structure of a large collection of documents. And topic modeling is a common text mining tool, right, used in a variety of domains, from literature to bioinformatics and other areas. So now that we have covered the tax, NLP tax, what could be the possible NLP tax? So here is a chart basically which lists some easy to hard NLP tax, right? So as you just move from up, down below, then we move from some easy tax. Spell checking is considered to be an easy tax because that's already an established problem and we have certain solutions there, right? And moving on, we have keyword-based information retrieval, topic modeling, text classification, information extraction, closed domain conversational agent, text summarization, question answering, machine translation, and open domain conversational agent, right? So as we move from up, way down below, we move from easy tasks and transitioning to some medium tasks and then hard NLP tasks. So natural language processing, as the name suggests, already has this language keyword there. So it undoubtedly tackles or deals with the language. Language is basically a structured system of communication that involves combination of its constituent components such as characters, words, sentences, right? And linguistics, that's basically a systematic study of languages, right? So earlier we said that one of the components, one of the sub-disciplines of that natural language processing deals is linguistics, right? Was linguistics, and essentially linguistics relates to the systematic study of any language. Systematic in the sense, as we already said that language comprises of basically, let's say, some different medium, right? For example, text, and this text would in return be composed of, let's say, words, sentences, paragraphs, documents, and so on, right? So we would need to basically study, do a systematic study of the language with regards to these different constituents of the language. So we need to understand some concepts from linguistics about the structure of a language, right? So there are different levels of analysis that needs to be done here, right? Starting from the word level and way up to the document level. So this is basically a building block. This figure represents the building blocks of the language and their applications. So as you see at the bottommost level, right? At the bottommost level, we have the phonemes. Which relates to speech and sounds, right? And phoneme is the smallest unit of any particular sound, let's say, okay? Speech. Phonemes, and then the applications would be speech to text. Speech to text, that essentially speech recognition, right? And then the speaker identification. So who is the speaker? That's also a potential application. And we also have text to speech. Text to speech, where provided a text, the system reads aloud the text, right? So that's at the phoneme level. Speech, and the smallest unit of any speech is a phoneme, right? Then moving on, we have these. Once this speech basically converts to text, once that speech transcribes to text, then we have this analysis at the word level, right? Analysis at the word level, where we have morphemes and lexemes, and morpheme is the smallest meaningful unit of a word. Right? Morpheme and lexemes are basically words, right? So from moving up, so we have the phrases and sentences, because words alone in isolated manner would not be very much meaningful, right? In order to have some value, some true meaning out of those words need to be arranged in the form of sentences, right? So in the syntax level, basically we have these phrases and syntax. So phrases would be a group of words, right? Group of words. It's not just a group of jumbled or random words, but some words which would give some meaning out of that, right? So we have phrases and sentences at the syntax level, and the applications would be parsing, right? We are familiar about parsing, right? So basically that parsing, the outcome would be the output would be in the form of a parse tree, right? In the form of a parse tree, and parse tree basically has a very crucial role in terms of representing grammatical sentences and to basically determine whether the sentence is grammatically correct or not, right? And in the same syntax label, we have this application entity extraction, which was named entity extraction, named entity recognition, named entity extraction, right? So from any text, we would be interested to extract the named entities, right? Which could be proper nouns, dates, and all those things, right? That comes under entity extraction, and then relation extraction, the relation between these entities. Moving up, so the next level is semantics. Next level is semantics. After syntax, the next level is semantic analysis, which refers to the analysis of a meaning, right? Analysis of a meaning. So we all know that, you know, even a syntactically correct program in a programming language, sometimes that would not lead to any output, right? Sometimes the output may be blank. So the same thing applies in here. And some text could be syntactically correct, but meaning-wise, they might not bear any meaningful things, right? Example is this colorless ideas sleep furiously, right? So that's an example. That is syntactically correct, but semantically does not tell us much, right? So so in order to decipher the meaning of any word or a higher level text, right, or the sentence, or let's say paragraph, we need to consider the context involved. Later on in the slides, when we discuss challenges of natural language processing, we'll see that ambiguity is one of the challenges. And natural language is full of ambiguities, right? We humans do a lot of parallel computation and parallel processing. We do have this common sense as well as world knowledge, and that makes it easier for us to resolve these ambiguities. But of course, for a machine, it's difficult. So we need to seek ways in order to teach the machine, in order to provide some intelligence to the machines to basically resolve these ambiguities, right? So ambiguity and all those stuffs, right? In order to resolve that, we need the contextual context, right? Context meaning something that occurred previously, right? For example, if I say the boy ate an ice cream, right? With respect to the word ice cream, right? Ate and the boy, these are context. The boy ate an ice cream, right? With respect to the word ice cream, all the previous words occurring could be related as context, right? So with that, the other building block of language is this context and contextual meaning, right? So because we wouldn't understand in the very first place if we just have this word BANK, for example, bank, which is a polysemous word, meaning to say that it has multiple meanings, right? It could be a financial institution or it could be a river bank, right? So in order to find out whether the intended meaning is a river bank or a financial institution, we need to have this context, previous context, or the context of the use of the word bank, right? So from that perspective, some of the applications are summarization, text summarization, where the contextual meaning is very important, right? It's very important to understand that contextual meaning here. Topic modeling that I already talked about earlier, right? In order to suggest a few topics, few relevant topics to the collection of documents or text, you need to, of course, understand the contextual meaning and all. Sentiment analysis, of course, there too, you know. Good is a positive word, but too good is a negative word, right? Good is a positive word, but too good to be true, that's a negative connotation in here. So, you know, NLP is interesting, challenging, at the same time, you know, it's ambiguous as well. So ambiguity is one of the problems of NLP. Okay, so from there, I just want to go do a walkthrough of the building blocks, right? Starting from phonemes. These are smallest units of sound in a language, and they are either single letters or a combination of letters, right? And these are particularly important in applications involving speech understanding, such as speech recognition, speech-to-text transcription, and text-to-speech conversion, right? So there are 44 phonemes in English language, whereas there are 35 phonemes in the Nepali language. That's just the information. Is an information. And these are basically English phonemes with sample words, right? Basically, you can see in the figure, we have consonant phonemes with sample words like bat, B, right? The sound B in bat and so on, okay? So morphemes and lexemes. So after we have done this analysis of the speech or phonemes, the next level, as I said, is the morpheme and the lexeme level of analysis. And morpheme is the smallest unit of language that has a meaning, and there are basically two types of morphemes. One is the free morpheme and the other is the bound morpheme. Free morpheme is something that has independent meaning on its own. CATS, cats, for example. If I give you an example of cats, then CAT, cat, is a free morpheme, whereas S is a bound morpheme or a suffix, right? Free morpheme, cat itself independently has its own meaning, whereas S, this bound morpheme S or the suffix, right, is a plural marker here, right? But for the plural marker S, right, it needs to combine with the free morpheme to indicate that it's basically a designation or purpose. Okay, so we have a free morpheme and a bound morpheme here. All right, so the morphemes are formed by a combination of phonemes, right? And we have these prefixes, suffixes, prefixes which comes in front of the word, right? Whereas suffixes which comes after the word, right? We also do have infixes which comes within the word, right? And circumfixes and so on. So there are, and these together these are known as affixes as well. So affixes could be prefixes, suffixes, infixes, and circumfixes. Okay. So lexemes are the structural variations of morphemes related to one another by meaning, right? For example, this word run and run and running, it belongs to the same lexeme form, right? And morphological analysis, basically what it does is it breaks down the word, right, and results in the stem. That's the maximum form beyond which we cannot really break it, right? That's the stem, right? And then we have these affixes, right? So this morphological analysis is very important for applications like the search engine, right? Earlier we were giving an example about information retrieval, right? Because what happens in here is that there are different forms of the same word, right? S-I-N-G sing, S-O-N-G song, S-U-N-G song, S-I-N-G-I-N-G-N-G singing, S-I-N-G. So all of these words refer to the word sing, S-I-N-G, right? So ideally, if we are looking for if you provide a keyword SING to the search engine, then it should return all the documents, not just the documents with where there is this word SING, but all the documents where you have these different forms of the word SING, right? So that's one of the typical applications of the morphological analyzer and the stemmer. So this morphological, these morphemes and lexemes, this serves as a foundation block for many NLP tasks such as tokenization. Later on, when we will cover the NLP pipeline, we'll be discussing tokenization, right? So in order to do some text processing, you need to tokenize the text. That's a tokenization in the word level would mean one word per line. So if you have a long text, you just tokenize the text in the word level as one word per line, right? In the sentence level, basically, if you have long paragraphs, if you have let's say long paragraphs with several sentences, then ideally in the sentence tokenization, we'd have one sentence per line, and I believe you'd be doing such exercises in your practical exercises or tutorials. Now tokenization, stemming, that's basically reducing to the stem or the root word, right? Khanu, khayo, khaireko, the root word or the stem is kha, right? So then learning word embeddings. Word embeddings has been very popular. You have heard about word to bake and globe and all those different word embedding schemes whereby the word vectors are basically converted to numeric format, right? Numeric form, and then you necessarily do some relational analysis, okay, between these different words that occur in the text. And of course, also part of speech tagging. So lexemes, morphemes, all of these basically they form a foundation block for different speech tagging tasks as well. So examples of morphemes, as you can see here, if you take the word unbreakable, right? Break is the stem. Break is the stem or the root word here, whereas on is the prefix and able is the suffix, right? Cats, cat plus s, right? So that way you basically do a morphological analysis of the words. Morphemes, morpheme examples. Right? And it's there, when you develop a morphological analyzer and a stemmer, there are different issues or challenges there. One of them is understemming, right? Where the stemmer does not stem out the words or the root word of the stem word as required. There is the case of overstemming, where we basically stem or reduce the root word more than required. That's overstemming. Okay. So syntax, every language has its own syntax, right? So when you write a program in the programming language, and when you just try to compile it, then if you have written the program confirming all the syntax of that language, then you would have zero syntax errors, right? The same thing applies in here. So we have a set of grammar that applies to a particular language, and syntax would basically, a syntactic analyzer, for example, would essentially analyze the text of the particular language as per the grammar of the language. Right? So our common approach is the parse tree representation. Okay, and we are familiar about parse trees, and where the sentence stays at the root of the tree, S, and then we have these noun phrases, verb phrases, and several other phrases as intermediate nodes, right? And then we have these parts of speech tags for each word, and we have these different words in the sentence at the leaf label, right? That would be typically our parse tree representation of the text, right? And parse trees are really important to basically to disambiguate, sometimes it also helps to basically disambiguate the meaning, right? So we have this very popular text or example, right? I saw the boy with a telescope, right? Whether the boy has a telescope or you are basically seeing that boy with that telescope, right? So with the help of a parse tree, we basically can disambiguate such situations, right? Because a parse tree would be different for, I saw the boy using a telescope versus I saw the boy with a telescope. Means I saw a boy carrying a telescope. The parse trees would be different there. Although the text would be the same. Okay. And entity extraction, relation extraction, all of these basically builds on the syntactic parsing or syntactic analysis. Right. So syntax of a language can vary from one another, and that means that we need to apply different approaches to do a syntactic analysis of the language. English, for example, we can follow the phrase structure grammar, right, or the context-free grammar proposed by the famous scientist Noam Chomsky, right? We can do that with the context-free grammar, phrase structure grammar. In case of Nepali and other Indic languages, for example, right, even some European languages, this phrase structure grammar is not very suitable to that, to do the analysis or the parsing. Instead, we need to go for some dependency formalism or dependency grammar formalism, right? And because it follows a Panini grammar, Nepali, Sanskrit, and other related languages, Indic languages, they follow this Panini grammar, right? And in that our languages is best analyzed by this Panini framework or dependency grammar formalism. All right. So let's look at this syntactic structure, right? Syntactic structure of two syntactically similar sentences. As I said earlier, so we start with the root as the sentence itself, right? And then we have this noun phrase and verb phrase as the intermediate nodes, followed by the respective parts of speech, right? There are 8 parts of speech in English, right? Determiner, noun, verb, preposition, right? These are all the different parts of speech that you see, which are basically aligned or assigned to the different words in the text. The girl laughed at the monkey versus the boat sailed up the river, right? So these are two syntactically similar sentences, and as you can see here, a parse tree representation of these sentences is basically displayed as well. So, okay. Context. I've talked much about context, so it's basically about trying to decipher the meaning of words or sentences or phrases or higher level of this text, right? Using the context in consideration, right? So, So we started with the phoneme label analysis, right, followed by morphological morphemes, right, that's the word label analysis, and then we moved up to syntax, then to semantics, and the next level is pragmatics, which basically deals with the context, right, and then we have this discourse as well, right, discourse level, which basically deals with that analyzing text at the document level or above, right. And when you are talking about context, what happens in here is that, for larger context, for example, you have been attending this winter school for the last 4 days and you are aware of what's happening in here, what type of lectures or what type of materials has been covered, we spoke on what, we will be speaking on what, so you are basically aware of the context. But even to me, for example, I am here for the first time today, right? And I'm not aware about the context. So if you talk something related to this school, so this winter school, which happened in the past, let's say 3 days, then I would not be aware about it, but your fellow participants of the school would be aware about it, right? So based on this, there are certain things which requires contextual knowledge or contextual meaning to understand the to make a fuller understanding of the text or of the utterances being presented. Okay. So NLP, why is NLP challenging? Interesting. It's interesting, of course. At the same time, it has a bit of challenge as well, and ambiguity is one of those, right? So look at this sentence, I made her a dog. I made her a dog. It can have multiple meanings, out of which 2 of the meanings are presented in here. The first one could be that you have basically cooked a dog, right? Whereas the other could be you made somebody to bend down to avoid an object. That's also, I made her a dog. So the ambiguity is because of this word made. I made her a dog. This word made. This verb made basically introduced the ambiguity. And ambiguity, basically resolution depends on the context in which the sentence basically appears, right? And ambiguity only increases with the figurative language or idioms, which is sometimes even difficult for us humans. So it's quite natural. It's quite natural to have these problems with the machine. So sentences like he's as good as John Doe, is as good as John Doe could be really problematic for the machines to understand. So let's look at some of the examples of ambiguity in the language, right? Here are certain examples, right? The man could not lift his son because he was so weak, versus the man could not lift his son because he was so heavy. Right? So it might be difficult to understand who was weak or who was heavy. And these are some of the examples, and the terms that introduces ambiguity have been basically highlighted in bold here. Okay? So besides ambiguity, another thing that makes NLP challenging is this common knowledge. We humans have a lot of common knowledge, lot of common sense knowledge, in other words, right? Which the machines does not necessarily have, right? You can look at the sentence: man beat dog versus dog beat man. Man beat dog versus dog beat man. We as humans, we know that it's very unusual for any man to bite a dog. And we will say that, okay, there is something wrong with this sentence. But for the machine, without that common sense knowledge, it will be difficult to basically differentiate between these two sentences: man beat dog and dog beat man. Okay? So one of the key challenges in NLP is how to encode all the things that are common knowledge to humans in a computational model. The other problem is creativity, of course. We humans are creative by nature, and the natural language can be spoken or written in many different ways. We can apply creativity here, and with creativity, that will create some problem for the machines to understand. Various styles, dialects, genres, and variations are used in language, and making machines understand creativity is a hard problem, not just in NLP, but of course AI in general. Diversity across languages. So the languages are diverse, right? Languages are diverse. The vocabularies are different, right? So if you have developed an NLP solution for one particular language, you cannot necessarily. It's not that you can necessarily port that solution to other language. That's not the case, right? And of course, building a language independent solution or language agnostic solution is also not that easy. Okay, so it's conceptually very hard, and to build a language agnostic solution or language independent solution, and building language specific solutions. Nepal alone has 100+ languages. If you didn't know that, then that's information for you. Nepal alone has 100+ languages. Just imagine how many languages we have all over the world. And if you try to, let's say, develop solutions for each and every language, then that's a very labor-intensive task. So, with that, we can basically now relate how this machine learning, deep learning, NLP are related. As you can see, AI is the superset. AI is the superset here with the largest, the circle in the Venn diagram there, right? Then we have machine learning, right? And then we have deep learning, right? That's basically specialization of machine learning, right? And then we have this NLP. We have NLP. So basically what you can infer from this diagram is that although there is some overlap, of course, there is some overlap between these disciplines. Each discipline are distinct in their own rights. Of course, we could apply machine learning techniques, deep learning techniques to NLP as well, but NLP also has its own different techniques, right? So that's something. They are related, but we should not, or we cannot necessarily apply deep learning or machine learning to each and every problem of NLP. There are certain areas where we should concentrate on utilizing the NLP techniques to solve NLP problems. But having said that, we can always supplement these NLP techniques with ML, DL, and other AI techniques. There are different approaches to NLP, right? There are different approaches to NLP. The very early systems were rule-based, right? Early systems were rule-based, or lexicon, or resource-based, right? And hence, these are also interchangeably, or in other words, also known as heuristics-based NLP. That's one approach. So early attempts at designing NLP systems based on building rules for tasks at hand. The good thing about these rules is that, since these are handcrafted by the experts, so unlike machine learning or deep learning, there is a very little chance of making mistakes, right? But the bad thing about these rules is that these are made by humans, and it's not possible to consider each and every possibility. It's not possible to consider each and every possible rule. So the thing is, if you have, let's say, developed 100 rules, soon you end up coming to a stage where basically the rules break. Meaning to say that there is a 101th case which is basically uncovered or which seems to have been missed by these rules. All right, so that's the beauty and that's the bad part of this heuristic approach. But still, even today when we are relying on this top ML and DL techniques and algorithms, of course, these heuristics or the rules or the lexical based or resource based also can basically have their own role in basically improving your results using the model developed using ML or DL. I mean, you could basically supplement them using these rules or heuristics. So, for example, one good example about this resource is this WordNet. WordNet, that's a very good resource developed by the University of Princeton. Right? WordNet is basically a lexical database of word relations. There are synonymy relations, right? Synonymy relations, hypernymy, hyponymy, meronymy, metonymy, several relations. And it's a very rich resource, of course, the early systems, and even today, WordNet is used in many different applications of NLP, including word sense disambiguation. Word sense disambiguation. Earlier I was giving an example of bank, river bank and financial institution. In such cases, you can basically use these resources like WordNet to disambiguate the words, right? Okay. There are, I've heard about Hindi WordNet as well, but I've not heard much about Nepali WordNet. Maybe some people are working on it, but which I might not be familiar about. Regular expressions are regex. That's a quite handy tool, right? Handy tool to basically look for patterns in the text. Right, so you could basically develop a regular expression, right? And these different scripting languages like Python or Perl, they have inbuilt support for these different regular expressions, even JavaScript, right? So that basically you can develop some rules or some expressions using which you can basically identify or find some certain patterns in the text. So that also all comes under heuristics, right? So context-free grammar, which is attributed to the famous linguist Noam Chomsky, right? That's used to model natural language, and that's also part of the heuristics, right? So rules and heuristics are a great way to build first person of NLP systems, because that way you would have developed an expectation. You develop some realistic expectation on the machine learning or deep learning model that you would be developing later on. Okay? And yes, as it is mentioned here, these heuristic based NLP techniques are generally used to plug the gaps in the system. What are the gaps in the system? For example, we have developed a fantastic machine learning model or deep learning model, and the model performs really well, but then you realize that there are certain areas of improvement, right? And that could be basically done using this plugging these heuristics in the system. Machine learning approaches to NLP, that's also it's getting increasingly popular. Right, there are well-established tasks which are solved by machine learning techniques, right? Earlier we were talking about this email spam classification, right? Which is quite established task. I mean, there are successful ML algorithms have been successfully applied for solving those tasks, right? Classification of news articles into some certain topics, news topics like sports or politics, right? So machine learning has been applied successfully for solving those tasks. Regression techniques, right? For giving a numeric prediction of, let's say, price of a stock, or let's say real estate, or all those stuffs, right? And then this unsupervised clustering algorithms, right, is essentially used for exploratory data analysis, EDA, also known as EDA, right? And for clustering similar documents, right? But irrespective of any ML approach, whether be it supervised or unsupervised, it consists of three common steps here. You extract the features from the text. Features meaning attributes. What are some of the features, or what are some of the attributes that would be helpful to classify the text, right? Then followed by using the feature representation to learn a model. You need to represent those features, right, to learn a model. And the third one would be, you need to evaluate and improve the model. So these are the three steps of any machine learning model that will be developing to solve NLP tasks or problems. So NAAMII, that's quite a simple to implement, fast to train, right? So that's fast to train and run this algorithm. So this is quite popular. It is based on the Bayes theorem, right? Bayes theorem. The algorithm assumes that each feature is independent of all other features. That does not, unfortunately, conform in reality. Because in any text, for example, machine learning, the two words machine learning, right? The second word learning has some association with machine, right? And they are not independent, right? But still with that assumption, NAAMII is quite successful for text classification problems. The other one is support vector machines. That's also quite popular an approach for a classification algorithm that's applied to text classifications as well. Right. So hidden Markov model, that's another model here. It's a statistical model, right? And it's applied for a wide range of tasks like parts of speech tagging, right? Or even speech recognition and all, right? So, hidden Markov model, HMM, is a statistical model that assumes that there is an underlying observable process with hidden states that generates the data. That is, we can only observe the data once it is generated. And an HMM, or hidden Markov model, then tries to model the hidden states from this data. So this is explained more. This is explained more intuitively with this parts of speech tagging task. Given a sentence, right? We just see the words. And the task is to tag each word with a suitable or appropriate parts of speech tag, right? And these tags, parts of speech tags, are hidden states, right? What we see is just the words, right? And here to basically the context would be important. Context meaning which words were tagged with which parts of speech earlier. Depending on that information, the successive or sequential word would be tagged with a particular parts of speech accordingly. Right? Okay. Yeah. So consider part of speech tagging of words and sentences. The assumption is that the text is generated according to an underlying grammar. We have underlying grammar for that language, which is hidden underneath the text. The hidden states are parts of speech that inherently defines the structure of the sentences following the language grammar. And we only observe the words that are governed by these latent states. Right? And HMMs also make the Markov assumption that each hidden state is dependent on the previous states. Each hidden state is dependent on the previous states, right? And we know that human language is sequential in nature. So we have a sentence which is comprised of words, right? There are left to right. I mean, the languages which move from left to right, and English, Nepali belong to that category. There are other languages which move from right to left, maybe Arabic. Languages following the Arabic script, for example, they move from right to left. There are certain languages which move from top to bottom as well, right? So HMM with these two assumptions are a powerful tool for modeling textual data. So HMMs are also quite popular models, right? Models for these solving NLP tasks. So this is just a graphical representation of the Markov model. So we have the text below, right? We have the text below, and we have the parts of speech tags assigned to each words in the text, right? Okay. From our discussions, we see that the parts of speech that has been assigned to this text are hidden, right? And once it is generated, based on those generated hidden states, based on those generated parts of speech tags, the parts of speech tag for a particular word is basically generated or predicted. There is another approach, very popular approach, conditional random fields as well, CRFs. This is another algorithm used for sequential data. And conceptually, a CRF essentially performs a classification task on each element in the sequence. So if it were to apply to parts of speech tagging itself, right? So basically what happens in here is that unlike HMM, for example, it would take into consideration all the previous context and not necessarily just the previous word. Okay. Since it takes the sequential input and the context of the tags into consideration, it becomes more expressive than the usual classification methods and generally performs better. Right? CRFs basically outperform SMMs for tags such as post tagging, which rely on the sequential nature of the language. So this is another model that's been basically used for NLP tags. Recurrent neural networks. That's now that we have completed. I mean, it's not exhaustive. It's not an exhaustive list of all the models for machine learning models and all those stuffs. But these are just a few, to name a few. And now we are moving to deep learning for NLP, right? Deep learning, which basically uses artificial neural networks, right? And that recurrent neural networks is quite a popular basically a model to solve NLP tasks. So RNNs have neural units that are capable of remembering what they have processed so far, right? And RNNs are powerful and work very well for solving a variety of NLP tasks such as text classification, named entity recognition, machine translation, and so on. Right? So RNNs can also be used to generate text where the goal is to read the preceding text and predict the next word or the next character. So RNNs are basically used for the RNNs which are part of the deep learning are also quite popular for solving a variety of NLP tasks. So this is just an unrolled recurrent neural network, right? So unfolded or unrolled recurrent neural networks. We have where we have the input and then the input, and we provide the input data, right? Input layer, right, and the hidden layer, and then the output layers. And then basically you could combine the outputs, combine the output of one particular neuron with the other, and in that is basically the strength of RNNs. So LSTMs are long short-term memory, another very popular deep learning model for solving NLP tasks. right? And this basically addresses some of the weaknesses of RNNs, in that RNNs are not capable of solving long-term dependencies of text. So text are necessarily lengthy or long text, right? So by the time we reach the n-1 text, then with RNNs you could basically lose some information from the previous states, right? So RNNs suffer from the problem of forgetful memory. They cannot remember longer context and perform poorly with long text. So LSTMs are basically improved version of RNNs, right? And gated recurrent units or GREs are another variant of RNNs used mostly for language generation. So this is just the architecture of LSTM cells. The other deep learning model that's been used increasingly these days for NLP tasks is this convolutional neural networks, or CNNs. Convolutional neural networks, as you must have known, is very popular. It's successfully applied to problems of computer vision, for example, or image processing, right? But these are also basically increasingly been used for solving NLP tasks these days. So this is just a CNN model in action, and how basically CNN could be used to solve certain tasks of NLP. The other very successful model in deep learning is transformers. Transformers, right? These are basically the latest entry in the league of deep learning models for NLP, right? And they have achieved the state of the art in almost all major NLP tasks in the last 2 years or so, past 2 years or so, right? This book that I'm referring to was published in 2020, so it's quite recent. So, so from that perspective, so transformers have started appearing in the late 2017, 18, right? So transformers model the textual context, but not in a sequential manner, not necessarily in a sequential manner. Given a word in the input, it prefers to look at all the words around it, known as self-attention. Self-attention, and represent each word with respect to its context, right? Even with humans, with humans, sometimes we identify that in a chunk of in a text, in a sequence of text, there are certain words or phrases which are more focal, which are more, which should be given more emphasis, right? Okay, so that way, this transformer can model such context, and hence have been heavily used in NLP tasks with the higher representation capacity as compared to other deep networks, right? Okay. So lately, large transformers have been used for transfer learning with smaller downstream tasks. Downstream tasks is certain tasks that you need to solve, right? And transfer learning, that's another paradigm of learning, whereby you essentially apply the learned model, which was initially developed for a particular purpose, to solve some other purposes. That's transfer learning. So transfer learning and transfer learning and transformer models have been basically used successfully in combination to solve a variety of NLP tasks. So these models are trained on more than 40 GB of textual data and scraped from the whole internet. Right. An example of a large transformer is BERT, this bidirectional encoder representation from transformers, right? And which has been applied to different downstream tasks successfully. Okay, so basically with this BERT architecture, we have two stages. We have a pre-trained model, we have a pre-training phase, and we have a fine-tuning phase, right? Pre-training, where we basically you use a pre-trained model or the BERT model, let's say, right? That you basically develop for some other purpose, right? You get some results out of that pre-trained model, right? Which might not necessarily be accurate because it was not developed for that particular purpose that you are experimenting right now. But what you could do is basically next step we could basically fine-tune the results of that pre-trained model, right? So this is a BERT architecture of pre-trained model fine-tuned and then tax-specific models. Autoencoders, right? That's also something that has been increasingly used in natural language processing, right? So autoencoder is a different kind of network that is used mainly for learning compressed vector representation of the input. So text, one complexity about text processing is that each word in the text could potentially be a feature or an attribute. So you have, let's say, tens of thousands of text, and you just imagine, and you have tens of thousands of attributes, potentially, right? So that makes it a requirement to basically go for some compressed representation of this text, right? Okay. So after the training, we collect the vector representation, which serves as the encoding of the input text. So basically, it's not just it's about making the representation as compact as possible, so that you efficiently can process the text, right? Right. So which serves as the encoding of the input text as a dense vector. Autoencoders are typically used to create feature representations needed for any downstream tasks. So autoencoders basically used for feature representations, right? Feature representation, feature extraction, feature engineering, these are quite interchangeable terms in machine learning or machine learning. So in autoencoder, the hidden layer gives a compressed representation of the input data, right? Capturing the essence, and the outermost layer, that's the decoder, reconstructs the input representation from the compressed representations. The variations of autoencoders, such as LSTM autoencoders, address the specific properties of sequential data like text. So as you can see here, architecture of the autoencoder. So we have autoencoder input nodes there, and the inputs are movie 1, movie 2, movie 3, and movie 4, right? That gets compactly represented in the hidden nodes, right? And then that basically now that compactly represented information about the movies would be again sort of decompressed, let's say, in the output nodes, and then that would be used for further feature representation or the like. So with all of this, we have covered all the different approaches for solving natural language processing tasks, starting from early rule-based systems or heuristic-based NLP, followed by machine learning, and then the deep learning, right? And deep learning is the latest hype, right? So there are trends that more and more people are interested to try deep learning models or algorithms for solving a variety of tasks, including NLP tasks, right? But there is this discourse that deep learning is still not ripe enough to solve all the NLP problems, right? And let's look into some of the reasons why this is the case. So overfitting on small data sets, all of us know that deep learning algorithms are data hungry, right? They require lots and lots of abundant amounts of data. And unless we use publicly available data, right, it is a tedious task, and it's not an easy task to have a decent amount of benchmarked or quality data. And there is no particularly there is no hard and fast rule about the size of the data set. So how, if often my students ask me, so what would be the optimum, what would be the good size of any data set for any machine learning or deep learning, and I would say that the more the better. That's the only answer that I have, right? I also don't have any particular number in mind that I can say, okay, this is the number that you would need, right? So for that reason, the normal thing is that usually the data for the problem you are trying to solve would be scarce. So you would have smaller data sets, and with smaller data sets and deep learning, applying deep learning techniques for smaller data sets, there is a big chance, there is a high chance that your model basically gets overfitted. Right? Overfitting, meaning that it basically performs well on the training data sets, right? But does not necessarily perform well with unseen or test data sets. Right. So DL models overfits on small data sets and subsequently lead to poor generalization. And one of the goals that we are trying to achieve using machine learning or deep learning is basically to improve generalization capacity of the model. Right. So this basically leads to poor performance in production. That's one of the pains. That's one of the pains of using deep learning for NLP tasks. Right. The other is a few shot learning and synthetic data generation. You have heard about zero shot learning or few shot learning, different modules, right, introduced by Facebook and other tech giants, right? So few shot learning with image processing, for example, or computer vision or the like problems, right? The problems, I mean, even with smaller amounts of data, or few shot learning, let's say, or I mean, the outcomes are quite good, right? But similar results have not been basically observed in NLP problems. Still, I mean, we cannot really escape from developing data sets, corpus, and all those stuff, right? So few shot learning is not essential for NLP, unlike in disciplines like computer vision, right? So that's for that reason as well. It might be difficult to readily go for deep learning to solve NLP tasks. Domain adaptation, that's another part. Domain adaptation, right? So we have already noted that DL models are not very good in terms of generalization, right? So hence, the models trained in one domain would not necessarily work for other domains. So domain adaptation is a problem in here. Other thing about deep learning models is there is an increasing trend of using this end-to-end models, right, where we provide input and then the model basically does something with those input, and then we have a let's say comparatively decent output as well. But the bad thing about it is that these deep learning models comparatively they tend to work as a black box thing. We don't necessarily have explanations, very good explanations about how we achieved or how we received this particular output. So interpretable models. So it's with the deep learning model, it's difficult to interpret the models. Right? Most of the time they work like a black box. That might be good for some, let's say, production systems, but for the academic community or scientists like us, computer scientists like us, that might not be adequate, right? So we would want to know the reason behind those outcomes. Common sense world knowledge, current DL models are still not capable of handling common sense. understanding and logical reasoning. So that's also a bottleneck here, right? Cost, it's costly in terms of money and time, right? Deep learning models are costly in terms of both money and time. So that is also one of the reasons why we might need to think twice before deciding to go for a deep learning model. On device development, most of the tasks required to deploy the model on the device itself, on embedded devices, for example, on mobile phones and so on, right? And well, I mean, these days these mobile phones or embedded devices are getting more and more powerful. That's good news for us, right? But that might not be necessarily accessible to all of us. So that particular aspect could be a bottleneck here as well, right? So these are some of the reasons. These are some of the reasons why deep learning might not be the right model for solving all the varieties of NLP tasks. All right. But having said so, this is not a generalized statement. This is not a generalized statement. Of course, it all depends upon the problems we are trying to solve, right? For example, transformers and all those things. These are really they have revolutionized the machine translation on all those problems, right? In that, the quality is getting. I mean, the quality output of these transformer models for the problems like machine translation has been really laudable, right? So, but for other problems, the takeaway message here is that you might need to analyze the problems that you are trying to solve, right? And right, so, and you need to basically go with a mix of all these different models, whichever feasible and whichever applicable. It could be a mix of heuristics. It could be a mix of natural NLP. It could be a mix of ML. Or it could be a mix of DLs. All right. So that's the very first part of my talk.